There's a lot of text on this one, so bear with me here. So what we just talked about, and especially in the find portion of the algorithm, if we wanted to start using trees on this, is going to eventually suck because trees are going to get bigger, and then even as we merge things together, the trees are going to get longer and longer every time we add more merges. And remember, as we get larger and larger trees, that means the find, not really the merge, but the find's going to take more work to get up there and get to see if we're what the root values are and see if they happen to be the same to make a cycle. We want to try to minimize that as much as possible. So what's going to end up happening is that we're going to create a quick union algorithm with a quick find and a quick merge, and we're going to cover the exact theory and a little bit of code of that here in a little bit, more theory than code, but still. So we're going to support fast unions, or each are set as a general tree. Now, this is not like a binary search tree or something like that. So your tree is going to have many, many, many kids. So that's maybe different than what you've seen so far in some of the examples. Although I think we're okay with that. You knew it wasn't going to be a binary search tree. But still, we wanted to make sure it's absolutely perfectly clear because of your usage of trees before we got to this point. So we want to try to flatten out the tree as much as possible so the find can do its job faster. The quick union data structure comprises of, frankly, a forest, which is going to look like it's going to look like a bunch of mini trees that have a lot of branches and not really something that looks like a binary search tree. It's going to be kind of as short as possible, but with a lot of branches. So that's where you come up with a collection of trees called a forest, because it is just that. The trees are merged by union operations, which we already explained, but again, the merge of those union operations won't be too hard because that part's not hard. It's the find part that we're really going to worry about. The quick union data structure is simpler than the general tree that you and I have been looking at because, well, all of these things that frankly, we haven't discussed until now. Notice all the pictures that we've gone over here. There's only one link in the node. There's only one value in the node. There's not a left and right pointer. There's all these things that right now we've actually taken for granted, but it's been drawn out basically in everything of this set of notes here. So it's a very simple node and a very simple tree. Matter of fact, there's only one direction that we can go into. So it's very similar, and that's why I kind of said linked list earlier. It's very similar to a linked list. So that's why we're going to be using the quick union algorithm on all this to kind of speed things up and also reduce the amount of code that you and I have to manage. So we're going to end up optimizing this to make these things a little bit more interesting and frankly a little bit faster for things to get done. Because we're hoping to get it pretty close to constant time, if you can believe that. Because again, if we're using this for a graph, that graph is already going to take a lot of time. Just get everything together and then you're trying to map things out. I've done many almost half-country trips. The map usually comes up pretty quick for me, unless there's an accident somewhere. But we're going to try to make this as quick as possible. So there's two optimization algorithms that we're going to cover here in a moment. The first one is a union by size, and then there's going to be some type of path compression. Now, even union by size, there's going to be two different versions on that, which confuses people, especially when they get tested. So be very, very careful about that. And the path compression is actually very, very easy. So that's a good news. So those are two optimization algorithms that we would use for our quick find disjointed set that we're about to cover here in a minute.